Thank you very much, and I'm very delighted to be here. I've not been over here at UAB very many times, and we're not that far away, actually, so it's really a pleasure to be here, and I appreciate the invitation. So I'm going to be talking about the program that we're really excited about right now that's within the umbrella of the CounterACT program, and novel Oxime antidotes for organophosphate poisoning, saving lives and saving brains. And I wanted to give you a little bit of background on organophosphates. They are very potent poisons, and I don't know what your background is, so they're anticholinesterases. You probably do know that. They arose originally during the Second World War in 1940s. They were originally developed as insecticides, and that occurred in Bayer Chemical Company in Germany, Bayer, the aspirin people. And Gerhard Schroeder of Bayer was the person that invented these insecticides. When the Nazi war effort heard about how potent these compounds were, they basically shifted that effort into chemical warfare agents. So they have been used in warfare a few times in the Iran-Iraq War and in the Syrian Civil War, and more currently in terrorist attacks. You may remember the Japanese terrorist attacks in Matsumoto in 1994 that resulted in 7 deaths from the use of sarin. And then in Tokyo the following year with 12 deaths and 5,000 hospitalizations, again with sarin. And the casualty count would have been far, far greater there if their chemists had been any good, but the sarin they manufactured was very, very impure. Very recently, there was an assassination attempt of Kim Jong-nam, the half-brother of the North Korean dictator, in the Kuala Lumpur airport, and I'm sure you remember hearing about that in the news, and that was with the agent VX. And then last year, Sergei Skripal and his daughter in the United Kingdom were poisoned in Salisbury with a Novichok agent. Novichok stands for a new chemical, and it's some of the new wave of organophosphates that are even more potent than the older ones. Curiously enough, Mr. Skripal was diagnosed originally as an opioid poisoning incident because opioid poisoning was quite common, and when they found out that he was a double agent for Russia and the United Kingdom, they started looking into chemical warfare agents. So this is a picture I kind of enjoy with Dr. Gerhard Schroeder in his laboratory in the 1940s, and again, developing one insecticide called Cystox that was on the market back in a number of years ago. So organophosphorus compounds are represented by this structure. It's a central phosphorus atom with 5 valences, pentavalent, tetracoordinate, 3 single bonds, and 1 coordinate covalent bond that is either an oxygen or a sulfur. If these are insecticidal compounds, they start out frequently as sulfur compounds and are metabolically converted to oxygen compounds. One group of these 3 is the leaving group that is most likely to come off when the compound phosphorylates something. So just a little background on opiate insecticides. Over 35 of them are registered in the United States at the present time and have a wide variety of agriculture and residential uses. The group has a large use in sales worldwide, and so many people are potentially exposed, and regrettably a lot of them in developing countries are used for suicides. There's a wide range of acute toxicity levels spanning 3 orders of magnitude. Parathine is one of the more toxic ones, and it has a red oral LD50 of 2 to 13, low milligram per kilogram range. Malathion that you may see in your neighborhoods for mosquito control being sprayed is in the gram per kilogram range. And again, this is a rather amusing picture, I think, of one of the earlier mechanical ways of spraying insecticides using a horse-drawn vehicle. And then the more current ones like the crop duster. This is a very dangerous occupation just in Columbus, very near where I'm, near Mississippi State University. One of the crop duster planes crashed just a few days ago, and it really mangled up the plane, and the pilot was actually able to walk away from the event, but that happens every once in a while. So here are some example compounds of some of the insecticidal organophosphates. Parathine is sort of the prototypical organophosphate insecticide, and it's very potent. Malathion is the one that they spray in your neighborhoods for mosquito control. Methylparathine is also quite toxic. Chlorpyrifos has been widely used in households and on crops. And dichlorvos is fairly volatile and is used in some fly strips that control flying insects in your house. So again, quite a variety of structures. The other main aspect of organophosphate chemistry that we're concerned with are the nerve agents, sort of erroneously called nerve gases sometimes, but some of them are volatile liquids, not really gases, and that is sarin that was used in the terrorist attacks several years ago in Japan, and then in against the Syrian citizens a few years ago. And then soman is an extremely potent one that's very hard to antidote. But some of the organophosphate nerve agents are also non-volatile liquids, such as VX, and that was the one that was used to kill the Kim Jong-nam in the Malaysian airport a couple of years ago. If you may recall, they co-opted a couple of young women to put the VX on their hands, and they ran up to him and put it on his face, and he basically died in the taxi before he could get to the airport. So these are very potent, not the airport, the hospital. So these are some of the older types of protective equipment that the military uses, and this is a little more modern way to try to protect some of the military that are known to go into battlefields that have nerve agents available. So here are some structures of some of the nerve agents. Sarin over on the left here, and soman, and then VX. So sarin and VX are two that have had some warfare or terrorist action recently. So how do they act? They inhibit the critical enzyme acetylcholinesterase by phosphorylating the active site serine, and the serine is very susceptible to phosphorylation by these organophosphates. This inhibition is very persistent. It lasts hours to days until spontaneous reactivation occurs by hydrolysis of the bond. However, one other thing that can occur is a process called aging, and it's in quotes because it's not an enzymatically mediated loss, but the alkyl group, one of the alkyl groups comes off non-enzymatically, and that prevents any kind of reactivation, either spontaneous by water hydrolysis or by any of the antidotes that we'll talk about in a few minutes. So the result of this inhibition is hyperactivity within the cholinergic system. So the buildup of acetylcholine in the synapses and neuromuscular junctions activates a tremendous number of systems in the body because the cholinergic system is so widespread. So this schematic kind of shows what's going on there. The serine residue in the active site of acetylcholinesterase is the target protein. What acetylcholinesterase does for a living, as you probably already know well, is that it hydrolyzes the neurotransmitter acetylcholine very, very quickly, at probably 25,000 or so molecules per second, and we have regenerated acetylcholinesterase that has a tremendous turnover rate. If the serine residue is inhibited by an organophosphate, such as para-oxime, then the leaving group, which in this case is paranitrophenol, comes off, and the serine group is phosphorylated with the remainder of the molecule. This phosphorylated enzyme can then recover with water hydrolyzing off the diethyl phosphate group in this case, and we have regenerated acetylcholinesterase. However, this process is very slow. It takes days or hours at least, and sometimes days for this to occur. If the aging process occurs, then one of these alkyl groups comes off, and this particular moiety then is refractory to any kind of reactivation. So this is an irreversible inhibition and cannot be restored. So what happens then? What are the signs and symptoms of a severe poisoning by an organophosphate? The term sludge is used for the clinical manifestations, mostly from the autonomic nervous system. We have salivation, lacrimation, urination, defecation, gastric distress, and emesis, so not a pretty picture. And I always wonder why people use these for suicides, basically, because it'd have to be a really, really awful type of death. Because of the activation of the muscles, then, we get tremors, and death would usually come after respiratory failure, and that's from several different sources. There's paralysis of the respiratory muscles, bronchiolar secretions, and these are really excessive, and so the foaming of the mouth that you sometimes see in some of the pictures of a few years ago of the Syrian civilians that were poisoned, that's from the bronchiolar secretions, bronchiolar constriction, and an adverse effect on the respiratory center in the medulla oblongata. So for all of these several sources then, respiratory failure occurs and death could occur. However, if someone does not die from these poisons, then seizures will usually occur, and if these seizures are prolonged and persistent, then there is permanent brain damage. And this is one of the things that we are trying to develop an antidote to combat, is the brain damage that occurs from these prolonged and persistent seizures. So this little graphic that I had somebody who had a little more artistic talent than I do had drawn for me the other few years ago. So the progression of signs and lethal poisoning by organophosphates be first nausea, diarrhea, and runny nose would occur. Headache would occur because of some of the vasoconstriction. Muscle twitches and difficulty breathing would occur as the respiratory system was started to be shut down. Tremors, convulsions, and finally paralysis of the respiratory muscles and breakdown of the entire respiratory system and death. And how fast does this occur? This can occur within minutes, basically. So some of these compounds are very, very potent and very, very fast. So what's the standard therapy for organophosphate poisoning? One of the absolute standard ones is an anticholinergic, an antagonist of the muscarinic acetylcholine receptors, and that's atropine, which, as you probably know already, is a belladonna alkaloid, comes out of the deadly nightshade plant, and it opposes the acetylcholine buildup at muscarinic receptors and largely can keep the person breathing. The second line of defense is an Oxime reactivator of acetylcholinesterase, and the currently FDA-approved Oxime reactivator in here in the United States is a compound called 2-PAM, and I'll show you what that is in just a minute. And then another thing that is used is an anticonvulsant, such as a benzodiazepine, to suppress the seizures. Diazepam is currently approved. The military is trying to switch over to midazolam for these seizures. But the deficiency in the standard therapy is that this Oxime 2-PAM, that's currently the FDA-approved Oxime in the United States, it cannot cross the blood-brain barrier, largely because it's a positively charged compound, and as you probably know, the blood-brain barrier usually restricts charged compounds. So if it cannot cross the blood-brain barrier, it cannot reverse the organophosphate inhibition in the brain, and therefore that does not get there's no therapy against the OP inhibition in the brain. So this is 2-PAM. Its other name is pyrrolidoxime chloride. This is the Oxime group here. This double bond NOH is the Oxime group, and it's a strong nucleophilic group, and it is able to attack the phosphorus that's on the acetylcholinesterase, and it removes that and actually forms a bond with it, so you end up with an oxime phosphate, and the enzyme activity is restored. Most of the effective oximes are pyridinium compounds having this positive charge, and therefore are restricted from the blood-brain barrier. So the overall objective that we've had is to identify a novel oxime, and I'll show you what that platform is in a minute, that can penetrate the blood-brain barrier and provide neuroprotection in addition to promoting survival. So we'd like to see an oxime platform that not only can save the person's life, but also can save the brain function. So just to assure you and everybody else that I talk to that we do not have actual nerve agents on campus, which is probably not authorized and it's not a good idea at any event, is we use a couple of surrogates for the nerve agent chemistries that we're interested in. So the sarin surrogate we have is nitrophenyl isopropyl methylphosphonate, or NIMP for short. So this is the structure of sarin here, and this is NIMP. And you'll see that the only difference is we've substituted a paranitrophenol group for the fluoride group. This is the leaving group, so when the fluoride or the paranitrophenol leaves the rest of the compound on the acetylcholinesterase, the remainder of it's the same. So this surrogate then is highly relevant for looking at our oxime reactivators because, again, the acetylcholinesterase is inhibited by the same chemical moiety. This is the VX surrogate we use, and the same sort of thing. The only difference is in this grouping here, which we substitute paranitrophenol for this, which is the leaving group. And so with the VX surrogate, nitrophenyl ethyl methylphosphonate, NEMP, we have the enzyme phosphorylated with the same chemical entity. So again, another very highly relevant compound. The other compound that we have reflecting insecticidal organophosphates is peroxon, and that's this particular compound. Parathion, the parent compound, would be a P-double bond S compound, and this is the active metabolite formed from P450 mediated activation. So this is our platform of novel oximes. These were invented at Mississippi State University. They are substituted phenoxyalkyl pyridinium oximes. Okay? So the substitutions here on the phenoxy group are various, and I'll show you a few of the ones that we're working on right now. The alkyl chain here is either 3, 4, or 5 carbons long. We have a U.S. patent issued in 2016 on this platform, and then last year we got patents in Germany, the United Kingdom, France, and Italy. We also got the compounds licensed to Defender Pharmaceuticals last year, and they are assisting us in developing these compounds. So we have probably over 100 in our library of compounds that were invented and created at Mississippi State. We've narrowed it down initially to 5, and these are the 5 that we were originally looking at. The ones that were most effective were either 4 or 5 in the carbon length chain here, and then these are the substitutions that are on the phenoxy group here. So I wanted to show you the summary of the results first, and then I'll come back to it afterwards, but I want to show you what lines of evidence we have accumulated that show that these compounds are effective in doing what that we wanted them to do, which is cause survival in our laboratory animal system and also protect the brain in those laboratory animals. So our initial experiments were at a high sublethal dosages of either the serin or the VX surrogates, and these were delivered intraperitoneally in DMSO. These are not very water-soluble compounds, so DMSO was used as the vehicle. And then the animals were subsequently treated with our novel oximes by the intramuscular route. And what we got out of these studies, and I'll show you the data in a minute, was a reduction in brain acetylcholinesterase inhibition at either 30 minutes or 2 hours after administration of the oxime, an attenuation of seizure-like behavior. And seizure-like behavior, we're calling it seizure-like behavior because we don't have EEG recordings, but they really look like seizures, and they are some sort of centrally mediated behaviors. There's also a reduction in brain glial fibrillary acidic protein, GFAP, which is a sign of cell damage in the glial cells. And we got no therapeutic effects by 2-PAM on any of these parameters. They would then ramp them up. We ramped our studies up to lethal dosages of either serin surrogate or VX surrogate or peroxon. The CounterACT program, as you probably know, is pretty directive in what it expects its grantees to do. And we were really afraid to ramp up to a lethal level because we didn't know whether our antidotes would be good enough. And we were very pleasantly surprised that our antidotes were really quite good at saving the rats' lives too. The OPs were delivered subcutaneously in multisol. Multisol is a biocompatible solvent that dissolves them quite well, and then subsequently treated with novel oximes, IM, and atropine, because at the lethal level, the animals do not survive without atropine also. What we got, and again, I'll show you the data, higher 24-hour survival with the novel oximes than 2-PAM in most cases, shorter time to cessation of seizure-like behavior with the novel oximes compared to 2-PAM, and neuroprotection with the marker NuN, which stains neurons. So this is our treatment paradigm for our sublethal dosage. We put in an OP such as NIMP at 0 time. The animals start showing seizure-like behavior at about 30 minutes, and that's when we administer the therapy. And that would be either 2-PAM or a novel oxime, and then the animals were taken down at 2 hours and looked for acetylcholinesterase inhibition. And this is what we got. With 2-PAM, as expected, we get no increase in acetylcholinesterase reactivation because we know it can't penetrate the blood-brain barrier. And then with these 5 down-selected oximes, we got some improvement in acetylcholinesterase activity, with a couple of them being up in the 30 to 35% range, which is really pretty impressive. We also looked at, again, at the sublethal level at GFAP, which is a marker for glial scarring and brain damage. We looked at that 4 days out from the treatment and looked at the piriform cortex as well as other tissues, but the piriform cortex is one of the sites of OP-induced seizure generation, and so that's a very critical tissue in the brain. So what we had here is we have the control animals with an arbitrary and integrated density, and Oxime 20, which is for the most part our lead oxime, showed no damage to the brain. NIMP, the serin surrogate, increased the amount of damage. NIMP with our Oxime 20 showed the same as the control, so no damage. With NEMP, the VX surrogate, again, we got some damage in the glial cells, and with Oxime 20 therapy, we got no change from controls. So no change in the GFAP following LP exposure. What did 2-PAM do? Looking at the piriform cortex and then also the dentate iris, with same sort of paradigm. With the control and the 2-PAM, there was no damage to the glial cells. With NIMP, there was damage. With NIMP and 2-PAM, no protection in either the piriform cortex or in the dentate gyrus. So again, we show that 2-PAM did not protect the brain, but our Oxime did. The treatment paradigm that we've used for survival of a lethal dose, ramping up to the lethal dose, was sort of similar. We give the organophosphate, either the serin surrogate or peroxime at 0 time. At about 30 minutes, they show seizure-like behavior. And at that point, we give them atropine and Oxime, either 2-PAM or our novel Oxime, or a combination of 2-PAM plus the novel Oxime, and then look at the survival at 24 hours. Not a very exciting parameters, the number of feet in the air divided by 4, basically, so not mechanistic, just counts. But we were very pleased that our compounds did very, very well with allowing the animals to survive for 24 hours. So let me explain the format of this particular graph here. We are comparing the survival with Oximes compared to 2-PAM. So the zero level here on percent survival means that if it was a 0, it's the same as 2-PAM. Anything above the 0 line is an improvement over 2-PAM. Anything below is not an improvement. And this black line at 25%, this is our milestone. As you probably know, the CounterACT program in parts milestones to progress. And we had to get a 25% or better improvement over 2-PAM in order to meet that milestone. And what we've got is our compounds 1, 15, 20, 55, and 55 alone on the left, and then in combination with 2-PAM on the right. And in almost all cases, we met the criterion for the milestone of 25%, and in some cases, we got some substantial improvement of survival with our compounds compared to 2-PAM. So again, we were really quite scared to do these lethal level studies, but we found that they did very, very well. And they're showing some broad spectrum efficacy here too. The gray bars are NIMP, which is the serin surrogate. The red bars are the VX surrogate, and the black bars are the peroxime. And so both the nerve agent chemistries and the insecticidal chemistries are protected by our novel Oximes. These are the graphs that show some of the seizure cessation data. These are Kaplan-Meier time to event graphs. And with 2-PAM, the animals, with the serin surrogate NIMP, with 2-PAM, the animals are seizing almost up to the time of 8 hours, 8-hour observation time. Going down here, just look at Oxime 1 by itself. A number of the animals quit seizing earlier than that, with 15. Some of them quit seizing earlier, 20 also quit seizing early. And some, but not quite so many, with 55 and 62. But we are interpreting this as some remediation in the brain, because this, again, is centrally mediated seizure-type behavior. And if the antidotes couldn't get into the brain like 2-PAM can't get into the brain, we wouldn't have seen any improvement. With peroxime, the insecticidal chemistry, we got the same sort of thing. The animals continued to seize for the entire 8-hour observation period. Again, Oxime 1 showed substantial improvement, Oxime 15 some, Oxime 20 quite a bit, 55 and 62 a little bit. So we were seeing with both the insecticidal chemistry on the previous graph and the nerve agent chemistry on the previous graph and the peroxon here, the insecticidal chemistry, an improvement in central behavior. We also got a supplement to our CounterACT grant to do some 24-hour survival studies with the actual nerve agent sarin. And what we looked at here was an LD85. There are 8 animals in each treatment group, typically, so one of them would survive with sarin all by itself without therapy. With sarin and 2-PAM, they get pretty good survival because 2-PAM is pretty good against sarin. These are our 5 oximes that we tested, 1, 15, 20, 55, and 62. And we got some survival with all of our novel oximes, not as much as 2-PAM, but still some. The 3 in red here are the ones that we down selected to after we went from 5 to 3. And just pointing out those are those 3. Even though the survival was a little bit disappointing, when we looked at their recording of the signs of toxicity over that 8-hour period, we really were pretty impressed. A 1 means no signs of toxicity up to about a 4.5 scale. The blue bars are at 0 time, and of course there were no signs of toxicity before they got the sarin. The orange bars are initial signs of toxicity right after they start showing signs, which is within 5 or 10 minutes. And then the gray bar is the amount of signs that they are experiencing 24 hours later. So here with 2-PAM, the initial signs and the 24-hour signs of anything that survived for 24 hours were still quite high. If we look at the 3 oximes that we down selected for, again, this is not statistically significant, but it does look like a trend that the initial behavior of these guinea pigs treated with the actual nerve agent sarin is lower with our oximes than it was with 2-PAM. And certainly at 24 hours, it's substantially lower than with 2-PAM. So even though the survival was a little bit disappointing, our novel oximes seem to show some efficacy of getting into the brain and at least suppressing some of the signs of toxicity in these guinea pigs with the actual nerve agent. So we down selected to 3 novel oximes out of those 5 that we were using. And I'm not going to show you all these data, but we have a lot of data that we looked at. We looked at in vitro acetylcholinesterase reactivation data, not just in the rat brain, but also in human red blood cell purified acetylcholinesterase, rat and guinea pig brain and serum. We looked at in vitro butyrylcholinesterase reactivation. Butyrylcholinesterase is a potential scavenger that's in the blood, and we looked at human, rat, and guinea pig serum for that. We looked at in vivo acetylcholinesterase data from rats and survival data from rats and guinea pigs. And with all of that in mind, then we've down selected to these 3, 15, 20, and 55. Again, there's 1, 5, and 2, 4s in the alkyl chain, and then these are the substitutions. If you take a look at these substitutions, they're adding a substantial amount of extra structure on the phenoxy ring here. So the philosophy behind this Oxime platform was that if we increase the lipophilicity enough by adding these extra rings and chains and all to the basic structure of an oxime, of a pyridinium oxime, then perhaps we could get them through the blood-brain barrier. It turns out that the efficacy is not related directly to their lipophilicity, but nevertheless, all of our oximes are quite lipophilic compared to 2-PAM. What we ended up using for testing our oximes against these organophosphates was the human equivalent dosage, not just a milligram per kilogram dosage, but the human equivalent dosage. So with 2-PAM is administered 25 milligrams per kilogram. That translates into 146 micromoles per kilogram. And we think that it's probably a more representative comparison of our oximes to 2-PAM if we're using the same number of molecules per animal, not the same weight, because our compounds are substantially bigger. So at this HED, 146 micromoles per kilogram, you'd administer 25 mg per kg of 2-PAM. With our oximes, 15, 20, and 55 would be 64, 69, and 72 because they're a lot bigger. So we are delivering a larger dose in milligrams per kilogram. So probably the most exciting data that we've got so far is a treatment paradigm with the lethal dosage of both the serin surrogate and Oxime, looking at histopathology as related to actual nerve cells. So sort of the same sort of paradigm there. We administer a lethal level of either the serin surrogate or Oxime at 0 time, at 30 minutes, about the time of seizure onset. We give atropine in either 2-PAM or novel Oxime at the human equivalent dosage, and then look at the brain sections at 4 days. And what we found with NuN, which stains the nuclei of neurons, with the serin surrogate at 4 days and the CA1 level of the hippocampus, the control animals showed an intact cell layer with NIMP substantial destruction at 4 days because of the seizures that were recurrent. With NIMP and 2-PAM, we still see a fair amount of damage in that cell layer. And with our Oxime 20, which is pretty much our lead, we do see the cell layer still intact. So substantial protection of the cell layer compared to the OP all by itself. So quantifying this, and the people that read the slides here were blinded to the treatment they were looking at, so they were not biased looking at the slides. The relative damage score from 0 to 3, control animals showed no damage, of course. With the OP, with either NIMP in the black bars or Oxime in the gray bars, we got damage score between 1 and 1.5. With 2-PAM, as expected, with no neuroprotection, damage scores in the same area. Oxime 15 was a little bit disappointing. It had damage scores that were still sort of in the same area as 2-PAM or OP alone. However, with Oxime 20 and Oxime 55, we had damage scores that were low enough to not be statistically different from the controls. So we got protection of both Oxime 20 and Oxime 55. Now this really kind of surprised us a little bit because it looked like Oxime 15 was actually a little bit better at the seizure cessation than Oxime 55, which didn't show a whole lot of the seizure sensation improvement. Oxime 20 has always been our lead for both. And we had some pharmacokinetics run on these 3 compounds. This was an IM dose that was delivered at the same dose for all 3 of the novel Oximes here at 50 mg per kg in male rats. Oxime 15 is the pink bar. It goes higher and comes down quickest. Oxime 20, the purple bar, lasts longer. Oops, did it again. And Oxime 55 lasts the longest. With the protection we got with NuN on the slides I showed you a few minutes ago, Oxime 15 was the one that did not protect. 20 and 55 did protect. And so we're thinking at this point that perhaps we get better neuroprotection with something that lasts longer in the system than the ones that is cleared a little bit earlier, faster. So I told you that our Oximes, our novel Oximes, are considerably more lipophilic than 2-PAM, and this is reflected by the half-life that was determined from the PK study. 2-PAM's lipophilicity, such as an octanol water partition coefficient, is 0.006. Oxime 15, 10 times more lipophilic. Oxime 20, even more lipophilic. Oxime 55, a lot more lipophilic. And this is reflected in the half-lives from the PK study. Oxime 15, half of it is gone in 2.5 hours. With Oxime 25, 2.2 hours. Oxime 55, about 14 hours. So again, how we're interpreting this is that if the compounds are in the bloodstream longer, here like 20 and 15, or 20 and 55, that they are able to protect the architecture of the brain better than the one that is cleared faster, which is number 15. So the neuropathology summary that I've got, we've got 2 markers there, GFAP, which is a glial marker, using the high sublethal serin surrogate. Oxime 20 was neuroprotective, 2-PAM was not. With NuN, which is a marker for the neurons themselves, Oxime 20 and 55 are neuroprotective, 2-PAM and Oxime 15 were not. So these are the 3 that we've down selected to right now. And one mechanistic study that we tried to do to see whether we could explain anything is that we assume that the blood-brain barrier is not just a physical barrier, but it also occurs because of the export transporters that are in the brain, one of which is P-glycoprotein. So we thought that the high efficacy oximes would be the worst PGP substrates, leaving them in the brain for a longer period of time with more time to reactivate acetylcholinesterase and remediate the poisoning. Low efficacy oximes would be the best PGP substrates with less time in the brain and less time to reactivate acetylcholinesterase. So we did a study with a number of the compounds. The red bars are the amount of reactivation. These were some of our better oximes for remediating acetylcholinesterase in the brain in the in vivo studies. The gray and the white bars here are the P-glycoprotein levels, and they are relatively low, as predicted by the hypothesis. And the reverse was seen with the least effective reactivators, the very, very low acetylcholinesterase reactivation with a couple of these and none with these at all, and much higher levels for the PGP efficacy. So it's perhaps that these compounds are getting into the brain but not being pumped out, the ones that are more efficacious for us. One of the things we're doing right now, which again is one of our milestones for CounterACT, is 24-hour survival with lethal doses of ceransurrogate and Paroxon with female rats to make sure that we don't see some lack or efficacy with females. So the black bars are NIMP in the male, and brown with the female, and then Paroxon blue and gray in male and female, with 2-PAM, 15, 20, and 55, and in most cases the males and the females are coming out about the same, so it looks like if these drugs were able to develop, they would be about the same efficacy in both males and females. So to summarize the results that I showed you initially, now that I've shown you the data, high sublethal dosages of the serin and VX surrogates treated with novel oximes, we got a reduction in brain acetylcholinesterase inhibition, an attenuation of seizure-like behavior, which was centrally mediated, a reduction in brain glial fibrillary acidic protein, which is a glial marker, and no such therapeutic effects of 2-PAM. With lethal doses of, again, a serin or VX surrogate or Paroxon, the insecticidal chemistry, we got higher 24-hour survival with the novel oximes than 2-PAM in many cases, shorter time to cessation of seizure-like behavior with our novel oximes than 2-PAM, and neuroprotection of the neurons themselves with NuN. So their overall summary is that our novel oximes continue to show positive results on survival and neuroprotection, with both reduction in toxic signs and histopathological results. The pharmacokinetic data that we have so far on the novel oximes provide information on the efficacy observed for cessation of seizure-like behavior and the protection from neuropathology, which seems to be related to how high they are in the bloodstream and how long that lasts. And female rats show similar improved levels of survival to males with a single oxime treatment. So I want to acknowledge the folks that are working in my group right now and the inventor of this line of chemistries. My co-investigator for many, many years and the co-inventor of these chemistries was my husband, Howard Chambers, who passed away nearly 3 years ago right now. So this is basically his brainchild for the lipophilic entity that is our Oxime platform. And then these are the folks that are working in my lab at the present time. And certainly we want to acknowledge the Department of Defense, which started this Oxime platform research through the Defense Threat Reduction Agency. That was then supported by our first UO1 NIH CounterACT grant, and then the third one there is our current UO1 CounterACT grant. But at any rate, what we think are some very promising data. We are hoping that we'll be able to develop the data sets that we can bring this to FDA and get approval. Everything really looks quite positive in terms of efficacy right now. You might ask why are these compounds still charged and getting into the brain, and we think we probably have a mechanism for that, is that they're not good substrates for the export transporters, and we're continuing to work. And I would see this as, if these are successful and we do get them approved, that this would be a fitting legacy to my husband who invented this chemistry. Thank you very much.